So hey guys, my name's Aman Muleba bearing the USN 1VE21IS003 and today my topic is pumping lemma from the subject ATC, which is Automata Theory Compiler and Design. Content. Introduction, statement, proof of the theorem, example, advantages and applications, and conclusion. Introduction. The pumping lemma is a fundamental theorem in formal language theory, a branch of theoretical computer science. It is used to prove that certain languages are not regular. The pumping lemma provides a way to demonstrate the limitations of regular languages by showing that for any sufficiently long string in a regular language, there must be a way to pump the string, generating additional strings that are also supposed to be in the language. Statement. If L is in regular language, then there exists a constant n such that for every string W belongs to L satisfying the following conditions. For each k greater than or equal to 0, x, y, k, z belongs to L. Mod of y is greater than 0 and x mod of xy is less than n. Then W may be divided into three pieces. W equals x, y, z. Proof of the theorem. If L is a regular expression, then some DFA M decides the language. If let P be the number of state in M, consider any string W belongs to L with length greater than or equal to P. The characters in W will cause the machine to transition through a number of state, eventually reaching an accepting state after the last character in. Because the number of characters in W equals or exceeds the number of states in M, the machine will pass through at least one state more than once or M reaches W. That is, the path that W traces through the machine has at least one loop in it. For the argument, we will use the first repeated state along the path. We will circle back around to that state for the first time before we have proceeded p characters. We decide our path into three parts. X is a portion of W which leads from the start to the first occurrence of the repeated state. Y is the part of W that traces the loop back around to the repeated state. Z is the final part of W that takes us eventually to the accepting state. M will now accept any string of the form xy to the power kz for k is greater than 0 because such a string takes m from start to the repeated state, goes k times around the loop back to the repeated state, and then runs from the repeated state onto the accepting state. This is the example where we have L is equal to open parenthesis a to the power n, b to the power n, where n is greater than or equal to 1. Advantages and applications. Language classification. The pumping lemma helps in classifying languages by distinguishing between regular and non-regular languages. Proof of non-regularity. One of the main application of the pumping lemma is to prove that a specific language is not regular. By assuming the language is regular, applying the lemma, and finding the string that cannot be pumped according to the conditions. It establishes the one regularity of the language. Development of more powerful formulas. The recognition that certain languages are not regular motives. The exploration of more powerful language classes such as context-free and context-sensitive languages. Conclusion. In conclusion, the pumping lemma for regular languages is a foundational theorem in theoretical computer science, illustrating the inherent limitation of regular languages by providing a pumping lemma length and condition for a string decomposition. The lemma allows for proofs of contradiction, demonstrating that certain languages cannot be recognized by finite automata or expressed through regular expressions. Its significance lies in its ability to rigorously establish the boundaries between regular and non-regular languages, making it an essential concept in the study of formal languages and automata theory. Thank you.